So I would like to introduce Dr. Daniel Cotton. He's an astronomer at the Monterey Institute for Research in Astronomy. He's originally from Australia, completing his PhD in physics in 2008 at the University of Newcastle, Australia. And then he went to Leicester.
Leicester, yeah.
Sorry, I knew I was mispronouncing it. In the UK, where he worked on space telescope instrumentation. He then moved back to Australia to the University of New South Wales to study the atmospheres of planets and stars. So that was fascinating. He also worked at Australia's largest telescope, the Anglo-Australian Telescope. And I'm not quite sure how he ended up here in the US, but he is currently working on polarization in stellar atmospheres and polarimetry instrumentation, which is part of what he'll be talking about tonight. So I'm really looking forward to hearing more.
All right.
Thank you.
Okay, thank you for that kind introduction. I am Daniel Cotton, as it said on the tin, and I'm here from MIRA to tell you about astronomy, specifically polarimetry and how we use that in astronomy. So for those of you who don't know much about the Monterey Institute for Research in Astronomy, it's a private, not-for-profit observatory that was founded in 1972 by recent graduate students who wanted somewhere outside of the university system where they could continue to do research and teach the public about astronomy. So education and research have been the dual parts of our mission for more than 50 years. The Institute runs a number of facilities, including a 36-inch research telescope in the Los Padres National Forest in what is one of the best observing sites in the continental United States. It's my understanding that the site that we have and this site were both runners for the Lick Observatory, and they chose this site because it was more accessible. So if you've come up the mountain, it gives you an idea of how remote the Oliver Observing Station is. We also have another smaller telescope that we operate at our offices in Marina when it's not foggy. Thank you. There are some people here from Monterey who know what I'm talking about. So best observing site in the US, possibly not so good. Right. One thing I should mention is that because we're not for profit, we're partly funded by research grants, but also largely by donations from the general public. And collectively, those people are known as the Friends of MIRA, and I always like to thank them when I give a talk. So they're the people that make this possible. We have a number of loose associations with the University of California and with Lick. I have a key scientific collaborator at the UC Riverside in Kimberly Bott, some of whose work will feature in tonight's presentation. We also observe at each other's telescopes. So I've been here observing with the 120-inch Shane telescope before. And just recently we had Dr. Noel Thenius from Cabrillo College come to our telescope and make occultation measurements. So he was interested in the recently discovered rings of the minor planet Quoror, and he was hoping to detect the change in density of those rings by the dip in light of a star as it passed in front of it. And we're keenly awaiting the final results on that. We also give talks at each other's institutions, so I'm here tonight talking at Music of the Spheres, and UC Santa Cruz astronomers often come and talk at our amateur astronomy meetings. I was reminded earlier tonight that we share a staff member. Our librarian is also working in your gift shop from time to time, so that's Joanna. And we also share an astronomer, actually. So one of our astronomers is Whitney Shane, who is the son of Donald C. Shane, who was a former director of Lick Observatory. So Whitney grew up on Mount Hamilton and is currently working with us. So if you're looking for an observatory to support, I know two good ones that you can send your money to. All right. All right, so tonight's talk is going to fall into sort of two halves. I'll give you some background information where I tell you what polarization is, how we use it in everyday life, a little bit of its history in applications in astronomy, before taking you through some of our latest results with the latest instrumentation. All right, so polarization is a property of light. It's probably one that you're not so familiar with because it's very difficult to discern with the naked eye. There's something called Harbinger's brush that if you look very carefully at in a very specific situation, you can kind of see a polarization effect. Most people are completely unaware of that. So most of the time, you're not used to seeing polarization with your eye at all. All the other properties of light we do see with our naked eye. And so in astronomy, we have the position of the light in the night sky is important to us. We call that astrometry. Or if you're doing it on a small scale, it's called imaging, where you look at the relative positions of different points of light. We also look at the change in intensity in light, so that we call photometry. And we spread light out into its constituent colours, into what we call a spectra, and that's called spectroscopy. So those are all things that you're regularly familiar with. Polarimetry is also a property of light. So usually when you see this diagram of a wave in an astronomy talk, it's because someone wants to tell you about spectroscopy, where the difference between the peaks of the wave tells you about its colour. So if you make these closer together, it gets bluer, and if you move them further apart, it gets redder. The wave in my presentation and in my hand is here for another reason tonight. It's because we don't just care about the distance between the peaks, we also care about the orientation of the wave. So in this instance, if we have a single photon, which is represented by this wave, an individual packet of light, then it oscillates in the up-down direction like this. Or it could oscillate in the left-right direction like this. Or in fact, any angle at all between 0 and 180 degrees. Now, polarization is an average property of light. So it's the average orientation of our photons. If we have a beam of light where all of our photons are aligned in this orientation, then we would call that 100% polarized light. If all the photons were randomly orientated such that there was no preferred direction, we would call that unpolarized light. And if we had a situation where, let's say, half the photons were in this arrangement where they were oscillating left-right like this, and the other half were randomly orientated, we would call that 50% polarized light. Okay, so now we know all about polarization. One way in which we use polarization in our everyday lives is with Polaroid sunglasses. So if we can't see it very easily with our naked eye, then we need some sort of tool. And in this case, the sunglasses can be described as a tool. So I happen to have here a set of glasses, which are not so useful to us because it's night, but nevertheless, here they are. That's what Polaroid sunglasses look like, much like most other sunglasses. However, Polaroid is a plastic, right? And I'll tell you more about that in a second. But what Polaroid sunglasses are really good for, apart from reducing the amount of light that's reaching our eyes, is for cutting out glare. So if you are driving and there's a slick surface, so fresh rain, for instance, then Polaroid sunglasses are good at cutting out that glare. Or, say, from a pond. So this is an image of a pond where you can see a lot of glare from the surface of the water. And if you were to put polarized sunglasses on, then you would see this. You could see straight through down to the bottom of the pond. So they're very useful for that. Also, seeing as how I'm from Monterey at the moment, I will mention that Monterey Bay is extremely good at generating glare. So Polaroid sunglasses come in handy there too. All right, so our Polaroid sunglasses, like I said, made of plastic. They're made of thin chain polymers. So a polymer is the carbon atoms arranged in a line that make up the plastic. And what we do is we draw them all out so they're all arranged in the same orientation, horizontal across the lens of the glasses. And what happens is that if we have unpolarized light from the sun, for example, then half of the light will have an orientation that's basically up-down, and half of it will be left-right. And the orientation that is aligned with the polymers will be absorbed by the glasses, and the other half will pass through, so that cuts the light down by 50%. Now, the reason the glasses are so good at cutting out glare is because if you have light reflected at a particular angle, then the light becomes polarized, so that the orientation of light is all crossways like this. So we're able to cut out pretty much all of the glare coming off the water, so long as the scattering angle is right. Okay, so not only do we get polarized light if we reflect light off the water, but we can also get it in the sky. So here we have an example of particles in the air, which are much smaller than the wavelength of the light. And if we have an incoming beam of unpolarized light like this, and it strikes a particle in the atmosphere, if it scatters in the forward direction, then that polarization will be largely maintained. But if it scatters at an oblique angle, then we increasingly get more and more polarization up until 90 degrees. So at 90 degrees, we get a maximum polarization. And that means that the blue light that you see from the sky, that's all scattered sunlight, is highly polarized, particularly if you're looking 90 degrees from the sun. So 90 degrees will be around here in this instance. You can see it could be up to 75% polarized. I have a picture here of it's a panorama of a sunset. So here's the sun setting across the water here. So we're looking in the sunward direction over here. And over here, we're looking away from the sun. And we're looking through Polaroid sunglasses. And we've aligned them in such a way that 90 degrees from the sun here, the sky is darkest. It's brighter over this side. So there's a good example of how of how you can see the sky polarization. Okay, and the Vikings were able to use this property of the sky to navigate. So they sailed their ships in Arctic oceans, where the sun would often skim the horizon and be just below the horizon. It was also often very foggy in those conditions. So quite often they couldn't see the sun, but they were able to figure out where it was in the sky by measuring the sky polarization. And they did this with something they called a sunstone. Now, the sunstone is a crystal, also known as calcite or calcium carbonate, arranged with a particular structure. And the structure of this crystal allows a beam of if I were to put a beam of unpolarized light into this crystal, then it would split it up into its two constituent orientations. So one beam of light would be in the up-down direction, the other beam in the crossways direction. So if you only put in polarized light and you arrange the crystal in the right way, you'll only get one beam out. But otherwise, you should get two beams. And if the light is unpolarized, they'll be of the same intensity. And if it's partially polarized, then they'll be of slightly different intensities. So they could look along the horizon and in the sky through this crystal and see one beam or two beam of various different strengths and use that to figure out where the sun was, even if it's below the horizon at night. That's extremely useful when you're trying to navigate. All right. So those crystals, those Icelandic spar crystals, are the same types of things that it's the same crystal that we use in modern polarimeters. It was also used by Etelon Malus, who was an engineer in Napoleon's army, and he discovered polarization in the modern sense in 1808, working in his living room with directed light from the sun. So he had crystals of calcite, and he was working in his living room trying to figure out what the properties of it was. And he was the first person to understand how it behaved particularly well. And no sooner had he done that than people started using calcite crystals and started looking at objects in the night sky with polarimetry. So Arago looked at the moon in 1811, just 3 years later. We looked at comets in the early 1800s. People looked at asteroids and figured out a relationship between the brightness and the polarization of asteroids. And Bernard Liot, the French astronomer, made a lot of observations of planets, in particular planetary atmospheres, in the 1920s. Here's an example of the polarization of the moon on the right. So you can see that the lunar mare, which are largely basalt and fairly smooth, are much more polarized than the surrounding highlands region. So there's a familiar picture of the moon and then the polarized picture at the top. A lot of these observations have taken us a long time to understand. In fact, some of them we don't still completely understand. Because what can produce polarization is quite complicated. It can be affected by the roughness of a surface. It can be affected by the size of the particles. If the particles are of the similar size to the wavelength of light, then the electronic properties of the particles are important as well. The atomic structure, so that the orbitals that make up that tell the electrons how to move around the material, are also important for trying to understand polarization. So the way we solve this problem is with what physicists call a complicated inverse value problem. And they call it that because they're too proud to admit then what they're doing is they're guessing, and then they're constructing a model and they're seeing if that matches their observations. But that is exactly what they do. Right. So one object that this approach has been successfully employed for is Venus, and in particular learning about the cloud tops of Venus. So some of you will have seen Venus through the 40-inch telescope earlier tonight. In visible light, it's opaque. The clouds block out all the light. Clouds are very difficult to determine the structure of spectroscopically because they have quite broad features. The clouds on Earth are very grey. That doesn't help us. Anyway, so let's see, where was I? Oh, right, okay. So Venus, like the moon, goes through phases. Half of the surface of Venus is always illuminated by the sun, of course, the same of any body in the solar system. And how much of that surface we see lit up when we look at it depends on the angle between the sun, Venus, and us. So tonight you'll see that Venus is at the third quarter, so it looks like this when we look at it from Earth. And in addition to this being a phase, it's also a scattering angle, right? So this is the angle that the light has scattered to the Earth from Venus and the Sun. So this situation applies here, except that the cloud particles are a fair bit larger, so the pattern is more complicated. And here are some observations that people took in the 1960s that show what the polarization of Venus looks like through the complete range of phases from 0 to 180 degrees, or as close as they could get without pointing their telescope directly at the sun. This is the infrared, this is the visible, and this is the UV. And using this information, Hansen and Huvier in 1974 constructed a model that matched that data that explained the clouds as a mixture of sulfuric acid and water. And this combination was later confirmed by spacecraft when they entered the atmosphere of Venus. So that includes the NASA Pioneer mission and the Russian Venera mission. This animation here is based on Hansen and Huvier's model, and you can see the blue lines here are meant to represent the polarization across the face of Venus. So the orientation is like this initially, and then it'll swap over and go the other way. And the length of the lines indicates the magnitude of the polarization. All right. Stars are a bit more complicated. So, or I should say at least that the polarization of stars is much smaller. The first person to measure or say they could measure polarization from the stars was Yevgeny Oman in 1934. He used a photographic technique, so I think he used a sheet of Polaroid, and took a photo of the stars of a star field, and then he rotated the Polaroid sheet and took another photo and looked at the difference. Later on, he said that he was probably optimistic about how sensitive his technique actually was. So really, the birth of stellar polarimetry wasn't until 1946, and it wasn't with observations that this began, but rather with a theoretical calculation. So the Indian astrophysicist Subrahman Chandrasekhar was the first person, so he's not taking a selfie, this is not a camera, just in case you were worried. Anyway, he approximated the atmospheres of hot stars as largely electron scattering. This is a pretty good approximation. That's a fair bit of what's going on. So they're dissociated electrons in the atmosphere. And he showed that the polarization of a star increases from the center to the edge. The reason that's the case, and here's a star I prepared earlier. The reason this is the case is because the photons coming to you from the center of the disk of the star have been scattered in the forward direction. So they're essentially unpolarized. The photons that are coming to you from the edge of the star have to come out this way and then scatter to you at 90 degrees. Right? The electrons are very small, so it's similar to the situation we had with the air on Earth. Okay, there's a small problem with this if you want to do any stellar polarimetry, and that is that the polarization, although it could be as high, Chandrasekhar said, as 11% here, it's also exactly 11% here and in the opposite orientation. And that's true for every different point on the disk of the star. So here, 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 and here, all the way around it. And that means that for a spherical star, our polarization is going to cancel to 0. Right? In order to measure some polarization, we need to break the symmetry of this star. We need to distort its shape in some way, add some extra scattering material somewhere else. Or, as Chandrasekhar suggested, block the light from part of the star. And I only made one balloon, so that's unfortunate. But he suggested doing this with binary stars. So imagine my fist is a second star. If it passes in front of part of the balloon like this, then the symmetry is broken. And a lot of people got very excited about this. They thought we can measure the properties of the photospheres of the stars, we can measure their polarization by looking at binaries. And they went out and they made polarimeters with photoelectric detectors for the very first time. And they didn't find anything. They didn't find this effect. And they didn't find this effect for two reasons. The first is that it turns out to be a much smaller effect than Chandrasekhar predicted. So the assumptions he made, whilst being completely reasonable, if you take all those extra effects that he neglected into account, every single one of them decreases the polarization in some way, so it's much smaller. And the second reason they didn't find anything is because the stars were being polarized by something else. And that something else was dust. Now, people already knew that there was dust in space. If you look at stars that are further away through a dust cloud, they look redder than they would be if they were closer, because the dust grains preferentially scatter the blue light out of our light path. However, what they didn't realize was that these dust particles were not spherical. They had some sort of elongated shape, so they might be needles or footballs or something like that. They're probably not footballs. They might be football shaped, they're probably not footballs. Right, and these dust particles tend to align to magnetic fields. Right, so all the dust grains, when they line up, act just like the polymer chains in the Polaroid sunglasses we talked about earlier. So the further away you go from the sun, the more polarized the stars look. And this is what Hiltner found in 1951 when he was trying to find binary polarization. It's also what Hall found only shortly after, because he and Hiltner were working together, and Hall remarked in his paper that they must have lost contact because Hiltner published without him. Anyway, we credit both of them. Hiltner and Hall both discovered this. And then people used this property of of light to map out the magnetic field of the galaxy. So this was done by a large number of people, including, say, Elsker P. Van Smith, who did a lot of the measurements in the southern hemisphere, just for instance. But that's not all we can learn about the dust. We can also learn about what sort of size the dust particles are, because in the 1970s, Chris Sikowski found that the interstellar polarization always has this sort of shaped curve. So this is 1 on wavelength down the bottom here. So it's basically has this sort of shape with color. And where the peak of this curve is, whether it's here or somewhere in this range, depends upon the size of the dust particles. And for the next several decades, this is basically what we use polarimetry for. We learned about dust in space, and we learned about dust around stars. So this is a T Tauri star that has quite a dusty atmosphere, and it's a young star, which is why it's like this. So we learned about early type stars by making these types of measurements. We could also learn about gas around stars, which because the gas can also be a scattering mechanism. You can learn about magnetic fields in stars and on the sun. Usually we use circular polarization for that rather than the linear polarization I've been telling you about. I'm not going to complicate the talk by going into circular polarization. And in the 1980s, J.C. Kemp, an American astronomer, measured the Chandrasekhar effect for the first and only time, right, in a binary star system. And he did this with one of the first high-precision polarimeters. The star that he measured this in, you might know, it's called Algol. So it's a famous eclipsing binary star. You can actually see the dip in light if you're very attentive with your naked eye. So it was known to the ancient Egyptians what the period of the binary orbit was of Algol. And Kemp did a lot of work on high-precision polarimetry of stars. Unfortunately, he died quite young, so he passed away in the early 1990s, and his work was largely forgotten by the astronomical community for some time after that. It wasn't for more than 20 years before people would next pick up the idea of high-precision polarimetry. And they did so because another American astronomer, Sarah Seeger, in 2000 wrote a theoretical paper that said if we looked at the combined light of a star and a hot Jupiter exoplanet that might be right next to it, then the small amount of light that's scattered by the hot Jupiter should be highly polarized in the same way the light from Venus is polarized. It's just that we can't separate the star and the planet because they're too close together. However, if the star itself is unpolarized, then in the net light, you should have a polarimetric signal of around 20 parts in a million. Now, this was, well, the best precision of polarimeters at the time was about 100 parts per million. So this was a fifth of that. And if you want to make measurements of this as that changes as the planet orbits the star, then you need a sensitivity even better than that. So most people said, thank you very much, that's a nice theoretical paper. This gentleman here, Jeremy Bailey, said challenge accepted and picked up Kemp's concept for high-precision polarimeters and has now built, I think, 5 different ones. One, or actually 3 now, with me. Here I am. It's a rare picture of me not wearing a hat. Right. Along with the rest of the team, this is Latina Kedziora-Chudza and Kimberly Bott, who I mentioned earlier, who's now at UC Riverside. And so the concept behind these polarimeters is to use a calcite crystal that splits the beam into the 2 orthogonal light polarizations. But the thing is, when you split a beam into 2, then the beams pass through different light paths in your instrument, and they end up on different parts of your detector, which have slightly different sensitivities. And if you're just looking at these by themselves, then the inaccuracies introduced by that means that you can't get down to this level. So what you need to do is you need to use a device we call a modulator to swap which beam is which. So it rotates the sign of the incoming polarization and flips which beam is perpendicular and which one's parallel. You have to do this really fast. You have to do it really fast because of the turbulence in the atmosphere that we call seeing. So it changes the character of the light just enough that if you do this slowly, and this is, say, the image of my star here as a hand, and then later on, it looks like this, or this, or this, or this. And again, the inaccuracies in your detector mean that you're limited in the precision that you can get. So we have to do that at hundreds to thousands of hertz, so that many times per second, in order to beat the astronomical seeing. And that's been done with a number of different instruments, including the Polish and Polish 2 instruments that Sloan Viktorovich has used at the Shane telescope on this mountain. It's also been done with an instrument called Planet Pol, and one called Hippie, or Hippie 2 as its successor, from which most of the data in this talk comes from. So this is Hippie 2 on the back of Myra's 36-inch telescope. Here's a close-up of it. And yes, there really are this many wires on the back of our telescope. And in this picture, it actually looks like there's less than there really is. So we have a lot of instrumentation on the back of our telescope. And we're more concerned with making observations than we are of tightening our cables. And this is a next generation instrument called Pixar that we can use on smaller telescopes. I'm not going to talk much about that one today, but it uses a CMOS camera as opposed to the more exotic detectors like photomultiplier tubes or avalanche photodiodes that some of these other instruments use. And they all use they earlier used these odd detectors because the CCDs that were very popular in cameras 10 or even 20 years ago only read out very slowly, so they're a very poor match to this type of requirement. CMOS camera, though, reads out quickly, and we can get around that. Okay, so these instruments were originally built to measure exoplanet polarization. No detections yet. We are very close. So maybe if I give this talk in a year, we'll be talking about the first detection of the clouds around an exoplanet with polarization, but not yet. However, we have made a lot of great discoveries about stars. And I'm going to be telling you more about some of those right now, so don't go away. So when you build a really sensitive new instrument, you usually try and do a survey where you look at all the same things that everybody's ever looked at before, and then you see if you can see anything that they missed. And that's what we did here. So we looked at, say, all the really bright stars that are very close. And we looked at the close ones because we didn't want to be influenced too much by the interstellar polarization. So we looked within, say, 100 parsecs, that's, let me think, 300 odd light years from the sun, where there's very little dust. And this diagram here is a Hertzsprung-Russell diagram. Some of you may or may not be familiar with it. If you're not, don't worry. This is the intrinsic brightness, or in some ways the mass of the star on this axis. And the spectral type, or the color of the star on this axis, from blue to red. And that also corresponds to temperature. So temperature goes this way. So we have the hottest, bluest stars at this part, and the cooler red stars over here. These are large red stars. These are sort of smaller red stars down the bottom. And the thing that's immediately obvious about this plot is that the things in this corner of the diagram are a lot more polarized, represented by the large circles, than the ones down here. So are these, but I'm not going to talk about them today. So the things in the top left-hand corner are all massive hot stars. They're all big blue stars that use up all their fuel really quickly and have very short lives. There's very few of these stars, in part because of that, right? And because there are so few of them, we know less about them than we do other stars. However, they're responsible for most of the energy input in the galaxy. So they produce a lot of photons that radiate energy, and that energy is absorbed by the interstellar medium. They also have very strong winds. So just as we have a solar wind of charged particles, these stars have even stronger winds, right? And so they're putting material back into the interstellar medium. And when they die, even more of that material ends up back in space in the form of heavy elements. And it's this material that goes into forming the next generation of stars and planets. So learning about the most massive hot stars is really important for understanding the evolution of the galaxy. Some of the most polarized stars in that diagram I showed you were something we already knew about. They're BE stars, where the E stands for emission. And in this case, these are rapidly spinning stars. They're spinning so fast that sometimes the material at the equator can reach escape velocity and exit the star. And when it does, it forms a disk around the star, which becomes an asymmetric scattering medium through which you can see polarization. The E in emission comes from the fact that the light from the star is absorbed by the hydrogen gas in this disk and then is re-emitted as light again. So if you look at a spectrum, you can see this great big peak here and another one over here that tells you that's happening. If you look at the polarization, you can see that goes way up as well when we have an ejection event. And then slowly this material falls back into the star and the polarization goes back down, the line in the spectrum goes back down. We don't know exactly what produces the ejection event, what triggers it. People have been wondering about this for almost 100 years now. So by looking at the polarization more sensitively, we hope to have more answers about that. In the meantime, though, some of the other things in the top left-hand corner of the diagram we have figured out. Some stars are rotating very fast, but they don't do that. They don't eject material. So we want to understand why some stars do that and some don't. Right? And the first step in doing that is to understand exactly how fast the star is spinning, because you want to know how close to escape velocity the hydrogen is at the equator. Now, if your star is like the sun and it has spots, then you can look at the change in brightness as the spots move across the surface, the surface of the sun, and measure that. Most hot stars don't do that. Most hot stars don't have spots. You can, usually what you do is you measure the spectral lines. So these black bits here are absorption lines. So materials in the stellar photosphere, mainly hydrogen, absorb the light, and when we spread out the light into its constituent colors, we have these black marks. Now, just like when you stand on the street corner and listen to an ambulance, when it's coming towards you, the pitch of its siren is quite high, and when it's passed you by, the pitch changes to lower, right? And so that's because the sound waves are compressed when the ambulance moves towards you, and they're expanded when the ambulance moves away from you. And just like that, when a star is spinning really quickly, this part of the star, the light waves are compressed because they're moving towards me, and over in this part of the star, where it's moving away from me, the light waves are spread out. So this light becomes bluer, and this light becomes redder. And so you can see there's a shift either to the red or to the blue, depending on which part of the star we're looking at. And if we take the whole of the star in aggregate, and what that does is it broadens the spectral lines. And if we measure the width of these lines, then we can determine the rotation rate of the star, almost. There's a complication. And the complication has to do with the angle that the star is rotating on with respect to us. Here's an eye, and it's looking in this direction, right? So if the star is straight up and down like that, then this is perfect, right? We can measure the rotation rate on this edge, and the one on the other side of it you can't see. But if the star was rotated all the way around and the pole was looking on, then you wouldn't see any difference from either side of the star, right? The star would be spinning around and around like this, so there's no part of it coming towards you and no part of it going away from you. And if it's in the middle, if it's tilted like this, then what we're measuring is not the total velocity, but the velocity times the sine of the inclination, where by sine, I mean the trigonometric property, right? So that's okay, but it doesn't tell us how fast a star is really spinning. For some stars, maybe half a dozen that are really close and really big, with a special instrument we call an interferometer, we can determine the shape of the star. We can construct an image. And when a star is spinning really quickly, the equator is effectively at a lower gravity, right? So it bulges out. And the Earth does this as well. So the Earth is wider at the equator than it is if you can measure pole to pole. Okay. This is a plot of the bright star Regulus, which is the brightest star in the constellation Leo. The other thing that happens with these stars is that the poles end up bluer and hotter than the equator. And again, that's an effect of the rapid rotation. When we did our survey, we noticed that Regulus was more polarized than the stars around it. Actually, this is an earlier survey, but when we did our surveys, we realized this star is a bit more polarized than it should be. And a long time ago, well, 1968 to be precise, these two gentlemen, Harrington and Collins, did some calculations where they showed that if you have a star that is rotationally distorted like this, then you've broken the symmetry, right? And because we've broken the symmetry, it should produce polarization. Now, if we know enough things about the star, we can construct a model to describe the polarization. And in this case, enough things means 5. If we have the average temperature, if we know its mass and say the polar radius, and we know the rotation in terms of the inclination and the velocity times the inclination, then we could construct a complete model of the photosphere of the star and map out exactly where the polarization vectors on it would be and take the sum of this and work out what our polarization is. In fact, we only have 3 of those things if you don't have interferometry. So what we then do is we construct a grid with 2 unknowns, and we can map one thing to the other. So for each one of these grid points, we create a spectrum that shows us theoretically what the polarization would look like as a function of wavelength. And we've made measurements at different wavelengths here. And when we do that, we get a good match for the star being at, well, it's at 86, I think, degrees inclination. And a velocity, a V-sin I of 318 kilometers per second, which translates to almost 200 miles per second at the equator. So if you were to drive to Monterey and back again in a second, that's how fast you would be moving on the surface of Regulus. That's pretty fast. I'll give you a second to think about that. Oh no, it's gone. All right. And you can see a little bit about what's going on here. So in this situation, if we look at the bluer light, where there's more blue light, remember, from the poles than there is at the equator, then the net polarization is perpendicular to the rotation axis. And in redder light, it's the opposite. The equator is a bit redder, so we've got more light from here, where the polarization is this way, and less from the poles where it's that way. And that's why you see the polarization change orientation. So we got good agreement with interferometry with Regulus. That shows we can measure that technique. Incidentally, Harrington here was, I think, one of the reviewers on our paper. Collins, unfortunately, had passed away. And I must say that at this point that I often feel very privileged to be working on things that people spent their whole careers working on and build up a body of knowledge that we're able to measure and verify their predictions many decades later. And sometimes you're rewarded with the fact that the people who made those predictions are around to see them come true. Regulus is not the only rapidly rotating star that we've looked at. Another one we've looked at in particular is called Sargass. It's a giant star, and because it's a giant star, it has a lower surface gravity, and so for the material on its surface is a lot less dense. It's a lot more diffuse. And that means the polarization is a fair bit higher, which is handy, makes it easier to measure. By measuring the polarization of the stars, we learn something about where they are in their life cycle. So when a star is born from the collapse of a cloud of hydrogen gas, if there's any type of motion in that gas at all, then it will set up a spin, right? So every star is born spinning. A lot of the most massive ones are born with really fast rotation rates because you've got all this material, large amount of material, and when it contracts, it's just like an ice skater bringing their arms in. So they spin faster as the material comes in closer to the center of gravity. And then because these stars have strong winds and material sometimes escapes the surface, it bleeds off angular momentum as it lives, and so it reduces its spin rate as it lives. And so these lines here are evolutionary models for single stars, and they show models for Sargass as the star ages, as it goes down this way. And you can see, here's our data point. It's nowhere near any of those. So what's going on there? Well, one possibility, the thing we think is most likely, is that Sargass is the result of a merged binary star. So when you have when you form a binary star system, and many stars are binaries, more than half of them, many more than half, in fact, then a lot of the angular momentum is stored in the binary orbit as well as in the rotation of the stars itself. And you get less winds coming from those systems as a result. But when the stars that later on merge, they are spinning faster than they would have been otherwise. So using this technique allows us to find merged binaries, which is important for understanding more about how the galaxy is going to evolve over time. Right? Okay, so that's the first of the new polarimetric mechanisms that I wanted to tell you about. The second one has to do with binary stars. I'm running a little bit behind. All right. So binary polarization has been seen since the 1950s. So you get this sort of characteristic curve with two bumps as one star moves around the other one. And the conventional explanation is that you've got gas entrained between one star and the other. This is true for Algol, and for that reason, people didn't think they can learn as much about the photosphere as they expected. So this material here becomes an asymmetric scattering medium, and so the polarization changes as one star moves around the other from our point of view. There is, however, a second explanation, and that is the stars are reflecting light. So if you look at any first-year astronomy textbook, it will mention nothing about this whatsoever. It'll say stars shine and the other bodies reflect light. Stars are producing their own light. They don't need to reflect. However, people have been speculating about binary reflection for well over 100 years. So Eddington in 1926 pointed out that the thing they were then calling the reflection effect was not actually reflection at all. It was absorption and then re-emission. So that's how long people have been thinking about reflected light from stars. The problem is that stars aren't very reflective. Also, the light from one star has to intercept the second one before it can be reflected, and there's not much of that. So if you're trying to look for this tiny amount of reflected light amongst the glow of two very bright stars, then if you've got no way to distinguish that light, then you're not going to have much luck. Polarimetry provides an answer to this question because the total light from each of the two stars will be largely unpolarized, but the scattered light will be very highly polarized, close to 100% in fact. So that when we look at this stuff in aggregate, we should expect a net polarization that we can measure. And in fact, we do measure that. So here is data from the binary star system of Spica. And Spica is interesting in this respect because there is no entrained gas. Spica is only 100 parsecs away. It's Alpha Virginis, so it's a very bright star that is very well studied. We know there's no gas from lots of measurements from other techniques. And yet, here's the same shape of the curve. This includes data that I took at the 3.9 metre Anglo-Australian telescope, the 60 centimetre Penrith telescope, which is also in Sydney, and a 35 centimetre telescope, something about this big, on a rooftop at a building at the University of New South Wales, which is relocated midway between the Sydney International Airport and the Sydney Cricket Ground, which has huge floodlights. So I'm very proud of this. The only thing that really caused a problem was when they had the vivid light festival and they used strobe lights. That was no good at all. Anyway, the point here is that this line is our model when we construct the geometry of the known Spica system, and it matches this curve extremely well. In fact, we have not fit this amplitude at all. This comes directly out of the known properties of the star. So this is very good evidence that stars reflect light. This is not the only binary star system we've looked at. This is another one called mu1 SCO that Antonia Mori measured the period of more than 100 years ago. And it does the same thing. It's a semi-contact binary. So there is some material that's extended towards one star from the other, but the binary reflection model also fits that data very well. So we can do this with lots of stars. That's cool. You might be wondering what use it is. So usually, when to measure the mass of a star, we use two pieces of information. We look at the Doppler shift of the lines as one star comes around the other one. So in a binary orbit, one star will be moving towards you at the same time the other one is moving away. And you get two curves that look like this. Again, the inclination is a problem. So what you get is the ratio of the masses of the two stars. You don't get the absolute masses. To find the inclination, the method that's most used is to look for eclipsing stars, and then you know that they're in the same plane, right? Because one of them is blocking the light from the other one. Yeah. The problem is that for the heaviest stars that we know the least about and that are most important for the evolution of the galaxy, there are only 8 known eclipsing binary systems that we've made measurements from. Maybe it's slightly more than that now. Maybe it's up to 12, but it's still not very many. I made this slide some time ago. So polarimetry potentially provides an answer to this problem because the polarized beam provides you with orientation information, right? So it can tell you what angle the inclination axis is on if you model it correctly. And so that opens up the possibility of measuring masses from many more massive stars. So that's something we're working on right now, and I'll be very excited to share the results with you in a year or so, I hope. All right. So that's what I wanted to tell you about today. So I've given you a background of polarization and what it's used for. Told you a little bit about how it's used in astronomy. And right now what I feel is the dawn of a new age of stellar polarimetry. We've been making high precision measurements for about a decade or so. And in that time, we've found new mechanisms for polarizing stars. I've shown you 2 tonight, but there are another 3 or so that I haven't had time to talk about. The 2 that I have shown you have allowed us to measure the true rotation rates of stars, and we've measured reflected light from binary stars, both things that have been very long-standing problems. And with this information, we were able to get a better understanding of the evolution of hot stars, and therefore a better understanding of how the galaxy will evolve over time. I'd like to finish by thanking my main collaborators whose work is included in this talk. This is Jeremy Bailey, Sina Kedziara Chudza, Kimberly Bott, Ian Howarth, Om Shastri, who is a Myra intern, a high school student who helped us build Pixar, Fiona Lewis, who is an honours student of mine, Ain de Horta, and Darren Mabel. Thank you very much.
We do have time for a couple of questions, if anybody wants to ask anything.
Yeah, go ahead.
You mentioned that this polarization to clouds of Venus and determine that it's made of water.
Sulfuric acid, yep.
Yeah. How do they determine what material it
So they know a little bit about Venus's atmosphere already. They know it's very hot and very dense. And they can take spectra and get indications of some things. So they use that basic information they've got to guess at what they think might be at different layers in the atmosphere. And then they do some complicated computer modeling. So they have to have the optical properties of each of those different things, and they pass the light in their computer model through subsequent layers of the atmosphere and look at how much is scattered and how much is reflected, depending on properties like the refractive index of the material and things like that. And so that gives them a curve that describes the polarization with changing angle, and then they go and compare that to the data. One thing I haven't told you is that I'm making polarimetric measurements of Venus right now for some of my collaborators who are interested in both trying to improve that model further, so they hope that more precise observations will help. But they also want to see if the polarization of Venus has changed, not just since the 1960s, but since Leo was looking at it in the 1920s. So they want to know if the atmosphere is evolving in any way. So it's an ongoing area of study.
You had mentioned T-Tauri stars and early stars in the early stages of their formation.
Mm-hmm.
But we didn't hear anything because he wasn't included in the presentation about what you might have found from polarization. So I was just wondering, is there anything exciting that we found yet?
So. T-Tauri stars are certainly not my field. They're my director's field, actually. But you can learn something about the character of the dust that surrounds the system, which has then, gone into making up the star. Related to this is debris disk systems, where you've got like a leftover asteroid belt or Kuiper belt. That's some of the material that didn't go into making the star, but is remaining. So we've also made observations of that, and you can get an idea for the particle sizes of the dust in those rings, and also you can try and match that to the materials that you think the dust is made of. That requires some very precise modeling. So that's the type of thing you can do with dust in planetary systems. And I'm not 100% sure, but I think that's some of what they were trying to do with T-Tauri stars as well. In addition to looking at how the polarization changed as the star spins and that type of thing, trying to understand about the environment around the star. Yeah, exoplanets, they're much smaller signals, so they're much harder to detect. But if you've got a star in a very dusty environment, then that's going to produce some higher polarization signals.
So you are looking at objects that are far away, but you've never said that polarization can change besides the dust. Is there anything else that can change it? Like the atmosphere, gravity effect, so on?
So there are some things. So the atmosphere can change the polarization slightly, in theory. So there's a thing, let me think, what's the Faraday effect, where if the star is, say, very low on the horizon, then it's passing through quite a lot of atmosphere, and that atmosphere can rotate the polarization slightly. No one has ever measured that. Because it's so small in optical light. I should say that people have measured the polarization of radio Faraday rotation, but not optical. So that's something that can happen. A colleague of mine believes that the heliosphere is producing a bubble, which is also modifying the polarization slightly. It's difficult to understand at the moment how exactly it might be doing that, and in order to, but the experimental results, the observations show that it could be, And to do that, they looked at decades worth of archival data of stars that are as close to us as possible, trying to look for very small effects to do with alignment of the position angles of those stars. So there are some possibilities. Also, I mean, the dust itself can change over time, right? If you've got moving dust clouds, then you might get a more dense cloud moving between stars that are far away and us. Again, no one's actually definitively detected that.
So mostly the polarization you get here is what is there. Now there's no Doppler effect or things that change your
I mean, most of the observations that I've talked about tonight are from broadband measurements. So we measure all of the green light, for example, or all of the red light, stuff like that. So Doppler effects are quite small in that, so we're not going to see much change in polarization shifting when you're looking in such a broad band. Yeah, so the effects that I've been talking about are intrinsic polarization. We've looked at mainly very close stars, so we don't have to worry about being drowned out by the interstellar polarization. But in principle, if you have a precise enough instrument, then you can detect some of these things from stars that are even further out.
One last question.
You mentioned that you use calcite in the instrument. Why do you use that instead of like a synthetic?
Calcite's better. You can get very pure crystals of calcite, and you could also use magnesium fluoride as the beam splitter. The difference is how widely separated are the beams. So we use magnesium fluoride in some of our instruments, calcite in others, and also how absorbing that crystal is at different wavelengths of light. So magnesium fluoride is better for ultraviolet, for instance.